They say that structural isomer, okay, and stereoisomerism should be considered when answering this question. How many isomers with the formula C5H10 have the structure involving pi bonding? Okay, so now I'll just put it over here. Okay, if I just put, okay, C5, okay, H10 involving pi bonding. Okay, why they mention involving the pi bonding? Okay, because I have taught you about whenever you have CnH2n, I told you that there are possibilities of having, if let's say I have C4H8, you can have, okay, you can have alkene, okay, you can have alkene, but there is another possibilities, okay, which is going to be a cyclic compound. I hope you remember this. If I just simply put the carbon in cyclic form and don't have any double bond, okay, so this is going to be another example which will follow this C4H8. So it means we need to be very careful. This is what we call functional group isomer. Okay, but here since they mentioned they want pi, okay, it means that we are ignoring this part. It means do not show any isomer that involves cyclic form. Okay, so they want the normal one. So here they are asking you to consider both structural and, okay, as well as stereoisomer, but they have given you the general formula. Okay, so if I put this, okay, if I put the longest carbon chain like normal, okay, will this be considered as isomer? This answer is correct. It is going to be considered as isomer. Okay, this is what we have learned just now. Okay, one of it. So now using this, let's explore everything. We have, okay, we have functional group isomer, but now we don't want to touch that. Okay, under structural isomer, we have positional isomer. So let's look at positional isomer. You have the same thing. You move the double bond over here. Now, if you move the double bond to here, it's still going to be the same. Both of them are the same. Okay, this is going to be position number 2. Okay, the double bond. So I am going to erase it. Okay, that's the another one isomer that you can get if you just follow the positional isomer. Now, once I have done this, okay, maybe start to break them. Okay, it means I'm going to do chain isomerism. So when I do the chain isomerism, so I just I don't actually touch the carbon double bond. So I just put carbon double bond over here. So I just put 4 carbon. Then when I break the CH3, I put it over here. Okay, I can put it over there. I can also put, okay, the C double bond C over here. The C, I put another C here. Still going to be different. Okay. Then, okay, I need to think, oh, can I break another one? Now, if I break another one, it's going to be C, 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 then double bond. Then where do I put the 2 carbon? One is already here. Can I put another one over there? The answer is no. Why? Because each carbon can have maximum 4 bonds. Now you have 5 bonds. Okay, therefore this one do not exist. So now I have 3 and 4. Is that all? Okay, no. You have to still think about this. Can I break this one? Okay, because the position is going to be at position number 2. So when I draw, I'm going to have at position 2. Then that CH3 I put here. If I put it here, it's still the same. Okay, so you can see the double bond, the position is different. Position number 1, position 1, now position 2. Can I do break another one? It's not possible anymore. Okay, so this is going to be the 5th. Okay, now all these are representing structural isomer. Okay, all this. If they ask you how many structural isomer that C5H10 has, the answer is 5. Okay, but now they are asking how many isomer in total. It means stereoisomer and structural isomer. So now when we are talking about stereoisomer, we have 2 types. Okay, we have cis and trans, and we have optical isomer. So the moment I see double bond, yeah, possible there will be cis and trans. Okay, but I think let's settle the optical isomer first. Let's find out whether any of these five, okay, has chiral center. No, 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 no. Okay, please do yourself. Yeah, no. Okay, I don't see any chiral center. No. Okay, this one is going to be three. You are going to have two CH3 groups. Okay, no, 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 no. Okay, please check. I don't see any chiral center. Okay, there's no chiral center. So it means there is no optical isomer. So let's focus on cis and trans. Okay, now if I look at cis and trans, this is going to be hydrogen, this is going to be hydrogen. One of the criteria to have cis and trans is the carbon attached to the double bond must have two different groups. Automatically, this one, same group, no cis and trans. Okay, no need to even see the other one. Okay, no cis and trans. How about this? H and then H, different group, different group, different group, different group. Okay, they have cis and trans. Okay, how about here? H, H, don't have cis and trans. Okay, H, H, don't have cis and trans. How about here? Okay, H, CH3. Okay, this carbon is okay. But this carbon, CH3, CH3, same. Not okay. Okay, not okay. So if you have this, now I have found out that out of these five isomer, okay, I have this isomer number 2. There's two variations of it. Okay. Now, do I consider this as one of the isomer? No need anymore, because this one example can be classified into two more. Okay. What is that? It can be cis and it can be trans. Okay, if you want me to draw, I can draw C double bond C, H, and then this is C2H5, this is H, this is going to be CH3, and it can be C double bond C, H over here, another H over here, C2H5, and this is CH3. You have two isomers. This is going to be cis and this is going to be trans. Okay, so here I have two versions of this. So how many total isomer that I have? Okay, let me use red pen now. 1, 2, 3, 4. This one can be counted as this, 5 and 6. Okay, so I'm not including 2 because I'm counting the 2 as cis and trans. So if you look at the question over here now, okay, the question will be, they are going to refer it as, okay, hold on. Okay, how many involving that? Okay, so this is going to be, okay, 6. And I have drawn, okay, everything for you just now.